All right. So number 9 is asking how long it takes something to go from here to Mars or something to that effect, right?
Something like that.
Hold on.
It's from Mars to here.
I didn't get to finish. You came up there and...
What chapter are we in?
So I didn't get to finish. Trust me.
7.
7. All right.
I'm just gonna read it. Just say right, because I probably want to say.
So trust me. Trust me, I know.
Honestly, I don't.
At least your answer doesn't say chemistry speak.
I need like some coaching.
It's all.
I didn't even finish it.
No,
I didn't even try it.
No,
It's like those made up numbers in math.
Did anyone do that correct?
I
Don't
swore.
actually-
Chapter what?
Yeah.
7.
Physics is
What?
not
Did
real.
Alright.
you, what did you get?
Yeah, physics isn't real.
Physics is real and chemistry is fake for real.
All right. Here we go. So your lab is all set. So we're just going to go over this kind of briefly. Maybe we can go through it in depth tomorrow, but I want to at least give you the correct answers. All right, so number 9 is asking, let's see. All right, average distance between Mars and Earth, 1.3. What do they mean by the average? This isn't chemistry or astronomy, but why do they say average distance?
Because it's not. It moves.
All right, because we're orbiting. They're orbiting. And did you know that the inner planets pass the outer planets?
You should have told me that.
So like we are orbiting faster than Mars is.
Yeah.
So we pass Mars at certain points. You know, Mr. Decker would probably be able to tell you
So
exactly when that
astronomy is
happens.
fake.
But if you're watching Mars while we're passing it, it looks like it's going the wrong way.
Isn't that
It's called
right?
retrograde motion.
Yeah. Mercury was in retrograde recently.
Yeah. Yeah, because so they pass us, right? Mercury passes us, so it looks weird, right? Because Mercury's going quicker.
I only know.
Anyways, yeah. So just a little astronomy there for you. That the average is because the distance changes based on orbits and stuff. All right. Now, how long would it take TV pictures transmitted from the Viking space vehicle on Mars surface to reach Earth? How fast do the TV pictures move? That's the only way you can answer this question. You have to know how fast it's moving. You two know.
The speed of light.
Yeah. All electromagnetic radiation moves at the speed of light in a vacuum. So in physics and chemistry, we always assume that the medium is a vacuum. Otherwise, you can't figure it out. Because then you have to take into account of the friction of air or whatever, water, whatever it's moving through, and that's just, I can't understand that either. So, it's moving 3 times 10 to the 8th meters per second. So if you can figure out how many meters there are between Earth and Mars, and you know how fast it's moving in meters per second, you just divide by the distance and you'll get, well, the inverted will be seconds to the -1, so you can just flip that. So in other words, think of the units. You have, who did this here?
Me.
Who's me?
Stephanie.
Good. So, there it is. Okay. So this is meters per second. This is
No,
Meters.
meters.
Yeah.
So 1.3 times 10 to the 8th miles is what they told us. So we're converting that to,
I know I should have messed up.
we have to convert this to meters. So I'm not sure.
She converted to kilometers.
Yeah, she didn't.
I'm sorry. I just
So,
don't
okay,
think
so-
it's right.
So that's that.
Yeah.
Okay. So then 1,000 meters are in 1 kilometer multiplied by 2.09 times 10 to the 8th kilometers. So kilometers cancel, so then we get that number.
No, you don't.
Oh.
She divided by. But I'm just all sorts of messed up.
Oh, so you divide it by 1,000.
That's why I was having. Oh yeah.
That's okay. You're on the right path. That's all right. It's okay. It's. So can I erase this?
Yeah.
Okay. So but her concept there, thought process is in the right spot. So that's good. So what did we get for that number? Sorry.
So wait.
You talking to me?
Anybody? What is this times this?
Wait, where did you get that?
Enough.
Hold on. What did I get? What?
2.09.
Oh, she didn't show that work yet. All right.
Okay.
There's
What's the conversion of kilometers to miles?
Oh,
It gives it to us.
1 mile.
1.3 or something.
that makes
1.61.
1.61 kilometers in 1 mile. How many kilometers in 1.3 times 10 to the 8th miles. So cross multiply, divide, and get that number. So that number's right.
I wrote the proportion. I had one.
Okay, now we convert kilometers to meters. So 2.09 times 10 to the 8th times 1,000. Marcy, what did we get for that?
2.09 times 10 to the 11.
Right. Meters. All right. Now, if we know this is how fast it's moving, it goes 3 times 10 to the 8th meters in 1 second. How many seconds if it's going this far? You can set up a proportion. Right? Does that make sense to everybody? If it's doing this many meters in 1 second, how many seconds will it take to go that far? So cross multiply, you're dividing this number by that number. And, anybody? The answer is?
690.
They put it in minutes, of course.
Like 11 and a half minutes?
They got 2.5 minutes.
That's not.
I got 6.
Here's the problem. They got 4.5 times 10 to the 10th meters.
How?
I don't know.
Again, see, this proves.
I don't know.
This proves answer C.
Because that's all right. That's all. The math is right.
He's gonna think I did that.
That's your problem.
Oh, here's why. I'm looking at the wrong problem. That's why. The answer is 700 seconds.
Alright.
690 you got? Yeah.
690.
700. So x equals about 700 seconds. So why did I give you this problem? It has nothing to do with these equations because, again, converting is an important skill in this class, as you've seen. And you're using the speed of light. Using the speed of light. So, make more sense? Yes? Pat, you with me on that?
Yes.
Okay. All right. 17. The answer is...
There's multiple.
Chemistry is fake for part C, apparently. Let's see, part A. 5,000 meters. Yes, that is correct. 5,000 meters. So, I'm not sure what's happening here.
Wait.
What is that?
I thought it wanted it in
Nanometers.
Yeah, I thought it wanted it in nanometers.
Oh, who did this? Okay. So, are you like using the E too? You're not a physics person though.
But don't use the.
It's
not the
that way when you
exponent.
type in a calculator,
It's not an
you don't
exponent
like
when you do
it.
the.
Right. Hey,
Yeah.
it's just, you'll see, you guys go to college, if you do anything with the science, the physics people always use E, chemistry always use
The
time
E
and
is so
I don't know
much
why,
easier than
it's the way it is.
Pat.
So anyways, how would we convert that to nanometers?
Times 1.
Yeah, multiply by 1E9.
So there's 1 times 10 to the 9th nanometers in 1 meter.
Yeah.
So that equals 5 times 10 to the 12th nanometers.
Bam.
Hey.
And then B, the answer is 4 times 10 to the negative 29th joules.
Oh
my god,
We
we got
just-
that. We just didn't round up.
Yeah, we just did round.
Did they give you the frequency?
Yeah.
Yeah.
Oh, okay, so Pat, V is frequency, and I think they gave it to you. So you just plug in what they give you.
Yeah, it was 6.0E4.
Yeah, so 6 times 10 to the 14th?
No, 4. It's just 4.
Oh, 4?
Yeah.
4 seconds to the minus 1. This is joules per second, so seconds cancel. You get joules here. So it's just Planck's constant times 6 times 10 to the 4th, because they give H is a constant, V they gave you, and that is 4.0 times 10 to the negative 29. 4 times 10 to the negative 29.
Yeah, we did.
Questions? Part C. We'll just erase that for a second. Let's see. Calculate the energy in joules of 1 mole of photons with this frequency. So we know the energy in joules, but that's for 1 photon. If you want a mole, so this is real important to understand moving forward. Remember when we were doing the square root 3 RT over molar mass? And one of the catches there is you needed to use the kilograms instead of grams. But then there was also that one question, I think it was on rubidium or something like that, that it wanted joules per mole or joules per atom.
Yeah, probably.
Anyways, if a question is asking for moles and energy per mole, it can't just be joules. It's going to be joules per mole. But that's not joules per mole, that's just joules. Because if you look at the units, joules seconds times seconds minus 1, you're only getting joules. So that's really for like 1 photon. Think of it that way. We want to know if this is the energy for 1 photon, what's the energy for 1 mole of photons, which is how many photons?
I googled it and I got Avogadro's number. Is that right? Of protons per mole.
Photons.
Photons per mole.
Yes. What did you Google?
How many photons in a mole?
Yes. How many photons in a mole? It's 6.022 times 10 to the 23rd photons. Yes. So, we know that. So 6.022 times 10 to the 23rd photons in 1 mole of photons. So if you have a mole of photons, that's how many photons you have. Okay, yes, good, we're good. Now what?
It said it equals to 1 photon over,
That number?
yeah.
Yeah. So I'm just going to rewrite it a little different. If there's this many joules in 1 photon, so that's essentially 1 photon's amount of energy it has, then how many joules are in 6.022 times 10 to the 23rd photons? So that's how we would figure this part C out. Okay, so you're doing this for 1 photon, part C, you're just multiplying that number by Avogadro's number, and you get an incredibly, or a much bigger number, 2.4 times 10 to the negative 5. So that's a big change, right? Because this is a huge number, multiplying it by a pretty small number. So you get 2.4 times 10 to the negative 5 joules per mole. So be careful of that. Anytime there's a question involving energy, if they ask for joules per mole, kilojoules per mole, you got to pay attention to units. How do you get mole on the bottom there of this? You would have to use Avogadro's number, because that's where that comes from. So be careful with that one. All right, 95.
Yeah, I didn't get to finish.
Okay.
I got the color.
What color? Blue. Yeah, it's blue. Good.
Ha! Loser. I got it too.
It said red.
All right. So,
Yeah, I told you. I didn't know I was gonna be right. So I just drew
all right,
it
here we
in,
go. So 95. We're going a little slower there, wow, but that's okay. 95. When a compound containing cesium is heated, photons with an energy of 4.3 times 10 to the negative 19 joules are emitted. Now, it doesn't say joules per mole. If it did, we'd have to cancel out the joules by dividing by Avogadro's number. I'm just trying to relate it to what we just talked about. So it just gives you joules, which means you can use E. All right, so you have E equals HV. We can plug that number in here just like Justin did. And again, the way Mr. McConnelly teaches, which is a good thing, it's just not, it doesn't occur to me to do this very often, rearrange it first. If that helps you, then do it. So it's looking for frequency, so frequency is E divided by H. That's what he did, so that's good. I think that's a good method. So this is what we're looking for. We're going to plug in the 4.3 times 10 to the negative 19. I know he wrote this, I'm just rewriting it, explaining it. Planck's constant, 6.63 times 10 to the negative 34. And remember, this is joules per second. Joules are canceled, so your frequency is seconds minus 1. That's what that is, 1 over seconds. And it is what he said, 6.48 times 10 to the 14th seconds to the minus 1, or 1 over second. Good. So that is the frequency. How does that help us determine the wavelength, Justin? What do we do now?
You can plug that in C equals lambda V.
Right. So now we're looking for this, right? So lambda equals C over V. So this is 3 times 10 to the 8th meters per second. V we just found. 6.48 times 10 to the, oops, not negative, 10 to the 14th seconds minus 1. So 3 times 10 to the 8th divided by 6.48 times 10 to the 14th. We get wavelength. That's in meters, though. So this is in meters. So seconds cancel. And we get 4.63 times 10 to the negative 7. And you're always going to get times 10 to the negative 7 for meter answers, every time. Because then we convert that to nanometers to look it up on a chart. Convert that to nanometers by multiplying it by 1 times 10 to the 9th. That gives us nanometers, and it's 463 nanometers. 463 nanometers, and that's blue. This is exactly what we're doing in lab. So it's good practice.
How do you know it's blue? Yeah.
Oh, you have to go to the book. If you go to page here, go to page.
Oh, it's page 280.
Page 280. Everybody go to page 280. Liam, you're not with me here.
Okay, so it's not like
Page 280. Page 280. All right. So if you go to 280, you look up 463. It's going to be in the blue range there, right? Blue, violet.
Is it 4?
What?
No.
Okay. I just want Liam to see it with his eyes. Page 280. Got it. Okay, so yeah, 463 is blue. All right, last one here. 138. All right, 138. Radioactive cobalt 60. Using nuclear medicine. All right, here we go. This is joules per mole. So now you have to get rid of the moles, get just joules, and then you're doing this. So once you get joules alone, plug it in here, you get your frequency, plug it in here, get your wavelength, and that's how we do 138. So first thing you have to do is take 1.29 times 10 to the 11th and divide it by Avogadro's number.
Did not do that.
Okay. Because we gotta get rid of that mole number. Let's see what the answer is.
He's fake, right?
But who's that, Liam? Yeah. I mean, you did everything right. You just forgot to get rid of the mole. That's
Just like physics isn't real.
So, what are the final answer we're looking for here?
frequency and wavelength.
Okay, so the frequency is 3.23 times 10 to the 20th. And the wavelength is, they put it in picometers for some reason. Oh, because it's so small. 0.929 picometers, which is 929 nanometers. Pico is times 10 to the 12th. So 929 nanometers. Yeah, that makes sense. 929 nanometers. So let me walk you through that, and then we'll start some lab. Stop bullying him.
I was just saying, girls be dreaming. Not too fast, but not too slow.
All right. Here's the concept. Where's the energy there, Liam? 1.29 times 10 to 11?
Yeah. Be in the fast side.
All right. Now, 1.29 times 10 to the 11 joules per 1 mole. We have to convert this just to joules. So I can't stress this enough. To use the E in E equals HV, you can't have moles. You got to get rid of that. So let's multiply this by 1 mole is 6.022 times 10 to the 23rd photons. So now you're going to have joules per 1 photon. That's really what the unit's going to be. So when you do this calculation, you get 2.14 times 10 to the negative 23rd joules. And actually, it's not photons, sorry, it's gamma rays. So it's gamma rays. So that's going to be your E. Now you plug this in for E equals HV. So this number divided by Planck's constant, 6.63 times 10 to the negative 34, gets you the frequency, which is, yeah, I just want to make sure I did that right. Something wrong with my number. I read that wrong. This is 13, not 23. Divided by that, you get 3.23. 3.23 times 10 to the 20th seconds to the minus 1. That's your frequency. Plug that in here. So cross those off. We get 3.23 times 10 to the 20th. So 3 e to the 8 divided by the frequency, and we get 9.29. 9.29 times 10 to the negative 13 meters. And if you multiply it by 1 times 10 to the 9th, to get nanometers should be 9, no, it's not 929. What would that be? So it would be negative 4. All right. Okay, that's why I did picometers. So if you do 1 times 10 to the 12th, that would be 0.929, right? I think. Or is it 14th? Sorry, I gotta look this up. The unit for pico is 12. Yeah, 12. Yeah. So if you multiply by 1 times 10 to the 12th, you get 0.929. picometers is what they have here.
How many nanometers is that?
Well, 12 puts us there. 9. It would be 929, right? Calculator's back there. I used a stupid one. Hold on. Who has a calculator handy? Double check me. Multiply that by 1 times 10 to the 9th.
Yeah, but I think it's right there. We have your weight.
Yeah, it's 9.29 times 10 to the negative 4th.
Okay.
Yeah, that makes sense.
I
You got an error. All right. Yeah, so the answer of nanometers, 9.29 times 10 to the negative 4th nanometers. That makes sense. Okay, here's the concept. Can you take energy that a question gives you, plug it in for E, and ultimately get a wavelength? If you can do that, you're in good shape. If they give you just joules, really all you're doing, if they give you joules, you're just plugging it in the two numbers. Plug and chug is what it's called. Anyone say that to you before?
No.
Yeah, all right. So that's kind of just what it is.
Yes, she did, bro.
What did you just say?
Plug and chug.
No.
Means just keep plugging in the equations, keep chugging along.
Said that last year.
All right.
That was the first time I was ever said.
Okay, so now, here's what we're doing in lab. You are going to take these LED lights, very, very little,